In this lesson, we're going to talk about linear approximations. And in the previous section, we talked about related rates, which is also an application of derivatives. And so now this linear approximation is another application of derivatives that I'm going to go through with you. A linear approximation uses the idea of the tangent line to make an approximation of a value of a function at a specific point. So the first thing I want to go over with you real quick is just a reminder of the difference between slope-intercept form and point-slope form. So slope-intercept form of a line looks like this, and this is what we've been using so far. Y equals mx plus b, where m is the slope and b is the y-intercept. And recall that we also have the point slope form of a line, which looks like this. Y minus y1 is equal to m times x minus x1, where m is the slope, and then I'll write it off to the side here. x1, y1 is any point on the line. So this here, y1, and this x1 is a point that you would plug in to the formula that's on the line. Now, the book uses the notation for tangent line in this section with point slope form. And they actually, what they do is they add the y1, that point, to both sides. So if you write it like this, and then you add y1 to both sides, you still have your slope, and then you plug in a point for x1 and y1. And then they also took it a step further and used function notation for this. So we would have the equation of the line, they use L of x is equal to your slope, and the slope at a point A on the curve would be the derivative at point A, so that's your slope, times x minus the x coordinate of that point that you're looking at on the curve, plus the corresponding y value at that point, which would be f of a. So this is the form of the tangent line equation that the book uses in this section. It's just different notation, but it's what we've been doing all along. Now, if I wanted to use the tangent line to make an approximation, I can do that as long as the x value that we're trying to approximate the value of the function of is close to that value that we use to find the tangent line on that curve. So if we look at the first picture here on the left, which is picture A, notice that we have the function 1 over x, that's in orange. So right here in orange, 1 over x, at least the part that's greater than 0. And then there's a tangent line at x equals 2. That's this right here. I'm drawing a pink line over it so you can see where it's at. And this is at the point x equals 2. Now, the second picture on the right, picture B, is this frame that I'm highlighting in green here. It's blown up so you can see a really close look at it. So you see the orange is the graph of 1 over x. And if you notice, the point that we're looking at here, the x coordinate is 2.1. X equals 2 is off to the left somewhere off of this grid. But if you see the tangent line that I'm highlighting here in pink like I did before, here's the tangent line. And so x equals 2 is somewhere over here. And when we look at the tangent line, if we look at x equals 2.1, the value on the function is super, super close to the value on the tangent line. So we can use that linear function, that tangent line, to approximate 2.1 because it's really close to x equals 2, which is where the point on the curve is hits that tangent line. So our first example that we're going to use to work through this, we are going to find the linear approximation of f of x is equal to square root of x at x equals 9. So that means we're going to find the equation of the tangent line at x equals 9 on the square root of x, so that any value of x that is really close to 9 can be approximated with our tangent line. And then once we find that linear approximation, which is our tangent line at x equals 9, we're going to use it to approximate the value of the square root of 9.1. Now you can see here, I'm going to try to highlight it. So here's the point on the graph of 9. So 9.1 is going to be somewhere really close right here on the tangent line that we're going to use for an approximation. Okay, so first we need to find our tangent line. And remember, although we're still finding the tangent line, we're using different notation in this section. And the tangent line at x equals 9 is going to look like this, right? X equals 9. 9 is our a value, the point of interest. So I'm going to take f of 9, that's our corresponding y value, plus the derivative at 9, which is our slope, and then x minus 9, because 9 is our x coordinate. Okay, so to find f of 9, I'm going to take 9, plug it into the square root of x, that's going to give me 3. To find f prime of 9, I got to take the derivative of the square root of x and plug in 9. Now, when I do that, I'm going to get 1/6. I'll let you guys do that as an exercise, but you should get 1/6 when you find the derivative and plug in 9. And then you have x minus 9. And then if you want to put it in slope-intercept form, you can distribute the 1/6 and combine like terms, and you can put it in mx plus b form if you want. Okay, so now we're going to approximate the value of the function at 9.1 by using this tangent line. So I'm going to write down f of 9.1. Now the key is to say that this is approximate, is approximately 3 plus 1/6 times 9.1 minus 9. And when we put that in on the calculator, what we're going to get is 3.0167. And that's if we round it to 4 places. Now, if we actually find the value, so I'm going to write down here the actual value of the square root of 9.1. If we plug that in the calculator and we round it, we're going to get, if we round it to, let's see, 4 decimal places, we're going to get 3.0166. So you can see that this is a really good estimate of the actual value. Okay, we're going to do the same thing for this example. And we're finding the linear approximation of sine x. And we're doing this at x equals pi over 3. So what we need to do first is find the tangent line of sine x at x equals pi over 3. So using the formula that we had before, we have f of pi over 3 plus the derivative at pi over 3 times x minus pi over 3, because remember, this is our point of interest, so that's our value of a that we're going to plug into the formula. Okay, so this represents our tangent line of sine x at the point x equals pi over 3. We have to actually find these values. If I plug in pi over 3 into sine x, I'm going to get the square root of 3 over 2. And if I take the derivative of sine x, that's cosine x, and if I plug in pi over 3, I'm going to get a half. And then I have x minus pi over 3. So here's our tangent line with our values plugged in. So this is our linear approximation. Now what we need to do is use it to approximate the value of sine of 62. So we want to find the approximation of sine of 62. Now because we're using radians to set up our tangent equation, what we need to do is make sure we transfer 62 degrees into radians. So remember, to do that, we're going to multiply by pi over 180. So we're going to approximate 62 times pi over 180, which is 62 degrees, by taking that and plugging it into our line here, our tangent line. And when we do that, we're going to get approximately 0.88348 if we go out 5 decimal places. Now you can see the picture here. Here's pi over 3, and then the square root of 3 over 2. That's this point here. So when we estimate 62 degrees, remember pi over 3 is 60 degrees. So we're going just a hair past 62. So it's in that same vicinity. So maybe somewhere right here, really close. So we can get a good approximation. Now, if you wanted to see what the actual value is for sine of 62 degrees, we can go to our calculator, make sure we're in degree mode, or you can leave it in radians and plug it in as 62 pi over 180. And the actual value of sine of 62 degrees, if we round it to 5 places, it's 0.88295. So it's pretty close. So here's the actual value, and here's the approximate value. So linear approximations can be used to estimate roots and powers. And in this example, we're going to find the linear approximation for the function 1 plus x all raised to the n at x equals 0. And that can be used to estimate the roots and powers of real numbers that are near 1. Because if I plug in x is 0, then I have 1 to some power. So if x is 0, you'll be able to estimate roots and powers that are near 1. And then once we find that linear approximation, we're going to use it to estimate 1.01 raised to the third, which is certainly near 1. Okay, so remember, here's our formula. We're going to plug in x is 0 because that's our point of interest. And we're going to take the derivative and evaluate it at 0. And then we have x minus 0 in here. So that's our formula for the tangent line. But now we have to find our values. So if I find f of 0, I am going to get 1. If I plug in 0 into the function f, I'm going to get 1, because 1 to any power, no matter what the value of n is going to be 1, even if it's like 1 to the 100 or 1 to the negative 5. 1 to any power is going to be 1. So f of 0 is 1. Then if I take the derivative, let's do that down here. If I take the derivative of that function, I bring the n down in front. I'm just using the power rule. I bring the n down in front. I leave that inner function in there. Then I decrease my exponent by 1. Then I have to multiply it by the derivative of the inner function, which is just 1. So here's my derivative. And then if I evaluate that at 0, I'm going to have 1 plus 0 is 1. 1 to any power is 1. And then when I take 1 times n, I'm going to get n. So if I plug in 0, I'll get n for the derivative. And then in here, I'm just going to have x, because x minus 0 is just x. So my linear approximation, once I clean this up a little bit, is nx plus 1. Now we can approximate 1.01 to the third by finding L of 0.01, since our function is 1 plus x, so our x should be 0.01. So when I add that, I get 1.01. And if I want my power to be 3, my n is going to be 3. So I have 3 times 0.01 plus 1, and that's going to give me 1.03. So we can say that f of 0.01 is approximately 1.03. If I wanted to find the actual value, I could take 1.01 to the third on my calculator and get that value is 1.03031. So here is our actual value, where the 1.03 is an approximation based on our linear approximation. So you can see how close these values are. So this is the actual and this is the approximation. So now that we understand linear approximations, we're going to actually start talking about what's called differentials. Differentials can be used to estimate the amount that a function value changes. When you have a small amount of change in the input, it tells you what's the change in the output. In other words, if we have a really small change in x, how does that affect my change in y? So if you think back to our notation where we say, if I take the derivative of a function, we have this notation, the derivative of y with respect to x, and then we state it as f prime, that's the derivative. Well, that dy, that represents the change of y on the tangent line at a specific point on the function, and then the dx, I'm running out of room here, dx represents the change in x on the tangent line. If I wanted to find out how the value of y changes when we make a small change in our x value, we can see what happens by using these differentials. So for this example, we're going to find the differential dy and evaluate it when x is 3 and dx is 0.1. So we need to take the derivative of y with respect to x, which is 2x plus 2. Now think of dy and dx as a value. So I'm going to multiply both sides by dx. So I have dy is equal to 2x plus 2 times dx. Now, if we're going to evaluate it when x is 3, so we're looking at the tangent line when x is 3, and we're going to slightly change the value of x and move over 0.1, and we're going to see what that does to the change in y. So we got dy is equal to 2 times 3 plus 2, and then the dx is 0.1. We're slightly changing x to see what happens to y. And so when we put that in on the calculator, we are going to get 0.8. So I'm going to try to draw a picture here. So if you look at the function x squared plus 2x, it looks something like this, just a rough sketch. And that at x equals 3, we have a point, and then we have the tangent line right here. Now, if I zoom in on this box right here, the picture that I'm going to get, here's the function. And then I have the tangent line that looks like this. It's going to be really close. Here's the point at x equals 3. Now, if I move over from x equals 3, if I move over 0.1, that's my dx, my dy is 0.8. So my dy is my differential and my dx is my differential. Now look at how close that is to the change in the function, because you're so close to that function because you're looking at the tangent line. If I look at the change in the function, let me pick a different color here. Let's pick purple. If I come over this way using purple, and I come up to find the change of y on my function, the purple, this part here, this is the change in x, and this is the change in y on my function. The dx and the dy is the change in x and the change of y on the tangent line. So that's the difference. Now let's do the same thing for example, or for part B. We're going to find dy and evaluate it when x is 3 and dx is 1. So we have dy dx is equal to, now I have to take the derivative of cosine, which is negative sine x. And then I'm going to multiply both sides by dx. So I have dy is equal to negative sine x times dx. Now, when I evaluate this at x equals 3 and dx is equal to 0.1, I have negative sine of 3 times 0.1. And when I put that in the calculator, I get negative 0.01411. So what this means is if I'm looking at the graph of cosine, and I look at on the graph of cosine at x equals 3, which is really close to pi, if I go over 0.1 to 3.1, then the change in y on my tangent line is going to go down 0.01411 approximately. Now here's a really good picture of what I was trying to show you. Because I'm not the best drawer, it's nice to have a printed picture like this from the textbook. So your line LX, that's your tangent line. And so if you notice, I'm going to highlight this in yellow. The change in X and the change in Y on the tangent line is called the dx and the dy. Now, if I look at the value of the function, that change in X, let me see, use a different color. So this change in X and this change in Y, if it goes all the way up to the value of the function, that's delta X and delta Y. This is on the function. Now, if you notice, if you want to actually find the change in Y, what is the change in Y? So that's the change in the height of the function when you add dx to your x value. You can find the change in y by finding the value of the function, right? If you move over from a to a plus dx, so you're adding on that small change to a, and then you evaluate the function at a plus dx, that'll give you the height or the value of y at a plus dx, and then if you subtract the value of the function at a, which is right here, you'll get that change in y. So the change in y is going to be the value of the function at a plus dx, and then you subtract f of a, and that will give you the change of y. And that should be really close to your dy. So in this next example, we're going to compare the change in y versus the dy. So if we want to find the actual change in y on the value of the function, that's my delta y, we're going to take that value of a where the tangent line is at x equals a. We're going to add the dx and evaluate the function at that point. And then we're going to subtract the y value at a, and then what's left over is going to have to be the actual change in y on the function. So in this case, our value of x is 3, and our change in x is 0.1. So to find my change in y, I'm going to find f of 3.1, because I'm at 3 and I move over just at 0.1. Then I subtract the value of f of 3. And when we plug that in, f of 3.1 into x squared plus 2x, and then I subtract f of 3, so I plug 3 into x squared plus 2x. When I subtract that, I'm going to get 0.81. So to find the value of f of 3.1, I'm taking 3.1 and plugging it into the value. I'm plugging it into the function. And then the same thing, to find f of 3, I'm plugging it in over here. And then when I subtract, I get 0.81. Now let's find the dy, the differential, which is the change on the tangent line, and let's compare them. So if I take the derivative of y with respect to x, that's 2x plus 2, and then I have to multiply both sides by the dx. And then I'm going to plug in 3 and 0.1. And what we got before when we did this was 0.8. So now, if you compare the two, this is the change on the tangent line at x equals 3. Next, the change of y, right, on the tangent line. If you move over 0.1, you go up 0.8. Now, if you look at the change of y on the value of the function, if you go over 0.1, you go up 0.81 on the function. So now that we're a little bit more comfortable with differentials, I'm going to show you how you can use differentials to estimate the error when you're calculating some volume. Specifically in this example, we're going to be talking about the volume of a cube. So it says, suppose the side length of a cube is measured to be 5 centimeters. So the length, the height, and the width is all 5 centimeters because a cube has all the same sides. And there's an accuracy of 0.1 centimeters. So what that means is whatever the measuring tool is that they're using, a meter stick or a ruler, each mark on that ruler or that measuring device is going to be worth 0.1. So even if you measure it to be somewhere between 2 marks, at most you're going to make an error of plus or minus 0.1. So we could underestimate by 0.1 or overestimate by 0.1. So I'm going to write down that the error is plus or minus 0.1. So we're going to use differentials to estimate the error in the computed volume of the cube. We're going to say that the change in x is going to be between 0.1 and negative 0.1. And remember what the change in x is. If we talk about the volume of a cube and the side is length x, then we cube it, right, to find the volume. So x represents the length of the side. And if we're saying the length of the side can change by 0.1 or negative 0.1, that means that's our error. So the difference in our x's could be either 0.1 or negative 0.1. So now if we look at the volume of a cube, that equation, and I take the derivative, that's dv dx, the derivative of the volume with respect to x, I'm going to get 3x squared. Now I'm going to multiply both sides by dx, so I get dv is equal to 3x squared times dx. So if I plug in 0.1 for dx, and I put in 5 for the side for x, what I'm going to get is 7.5 centimeters cubed. If I overestimate by 0.1, this is saying that the volume is going to be overestimated by about 7.5 centimeters cubed. Now, if I change this and I just put a negative 0.1 here, so I underestimate it by 0.1 centimeters, then that means I'm going to underestimate my volume by 7.5 centimeters cubed. So now let's actually compare this to the change in the actual volume. So if I find the volume at 4.9, so that means I underestimated the side of the volume by 0.1 because it's supposed to be measured at 5, but we underestimated it by 0.1. If I take 4.9 and I cube it, I'm going to get 117.649 centimeters cubed. Now, if I overestimate by 0.1, I'm going to get 5.1 cubed, which is 132.651 centimeters cubed. Now, if I find what the volume should be right at 5, if I actually measure it accurately, I take 5 and cube it, and that gives me 125. So my change in my volume is actually going to be between 7.651 and negative 7.35, because if I take my overestimation, which is the 132.65, and I subtract the 125, that difference is going to be 7.65 centimeters cubed. If I look at my underestimation and I take 117.649 and subtract 125, that's an underestimation by 7.351 centimeters cubed. So we estimated using our differential. We said our dv, instead of the change in v, the actual v that's on the function, we used our differential, that's the approximate change on the tangent line. We said that it would be 7.5 at most, or underestimating at 7.5 centimeters cubed. So you can see that this is a really good estimation of the error in the volume. In this last example, I'm going to show you how to compute a relative error, which is an error based on percentage. So we're going to use the same technique we used in the previous example, and then we're just going to find out what the error is in terms of a percentage when we compare it to the actual value. So this example reads, an astronaut using a camera measures the radius of the Earth as 4,000 miles with an error of plus or minus 80 miles. We're going to use differentials to estimate the relative and percentage error of using this radius measurements to calculate the volume of the Earth, assuming that the planet is a perfect sphere. So the first thing we're going to do is, since we know that the change in the radius of the Earth, which is going to be the error, is going to be plus or minus 80. So I'm going to list that down as dr is less than or equal to 80 or greater than or equal to negative 80. And then because we have the volume of a sphere is 4/3 pi r cubed, we can take the derivative of the volume with respect to r, which is dv dr. I bring the 3 down in front. The 4/3 pi is a constant, so I bring the 3 down in front and multiply by 4/3 pi, and I'm going to get 4 pi r squared. I multiply both sides by dr, so I have that dv is equal to 4 pi r squared times dr. Now, if we're going to estimate that the radius of the Earth is 4,000, we're going to get 4 pi times 4,000 squared and times our error, which would be 80 if we overestimate. If I underestimate, I'm going to have 4 pi 4,000 squared times a negative 80. So I know that my dv is going to be between 4 pi times 4,000 squared times 80 at most, and then definitely bigger than 4 pi times 4,000 squared times negative 80 if it's an underestimation. So my change in volume is going to be between these two values. So I could put this in on the calculator and find the actual value, but I'm not ready to do that yet because I want to actually now find the relative error by taking and dividing both sides by the actual volume. So I have 4/3 pi 4,000 cubed in the denominator. So I'm taking the error and divide it by the volume. And I'm going to do the same thing over here. Here's the error divided by the actual volume. So I'm going to take 4/3 pi times 4,000 cubed. And then, of course, I have to do it to the dv as well. So I have 4/3 pi times 4,000 cubed. So that gives me dv divided by the volume. When I put this on the calculator, it's a big mess, but we can handle it. 0.06 at most, and negative 0.06 for the smaller value. And if I change this decimal to a percentage, my error in terms of a percentage, so I'll call it the relative error, is going to be plus or minus 6%. So it's the same technique we used before, but then we divide by the actual volume or the actual measurement of whatever it is that we're dealing with to find the percentage of the error.